So, hi everyone, I'm Prashanth. I'm an AI engineer at Kùzu. I'm going to be talking a bit about Graph RAG, but specifically in terms of terminologies and the examples that have been documented in recent times. And I know there's another talk going on in parallel right now about Graph RAG. So my focus here is to understand the internals of these systems and explain a framework of thinking about these systems in a way that we can build them. So without any further ado, I'll get started. So I know Graph RAG has become an incredible buzz term over the last few months. And in this talk, we're going to go over what exactly Graph RAG is, like what are its components. The one thing we need to convince ourselves of is, do graphs measurably improve RAG in practice? And can we devise a framework to better understand Graph RAG? Namely, what is the graph in Graph RAG? What do the nodes and edges represent? And how is the retrieval process in Graph RAG different from traditional RAG, which we'll go over in some examples. And then what role do databases play in this process? So first and foremost, let's look at retrieval in the age of LLMs. We all know the ChatGPT interface, which is you send a query in natural language, you receive a response in natural language, and the data goes through the LLM. Now, you cannot easily retrieve private enterprise data, as you can imagine, from these systems because they were not trained on your private enterprise data. So there comes about RAG, which is you have unstructured data and structured data, which is private to your enterprise and your organization, and you collect them and store them, and you build a system on top of it that allows you to query that data using natural language. So let's take a little bit of a deeper look at what we call traditional RAG. And if you're familiar with RAG, you'll find this diagram very familiar, which is you typically have data that you chunk, and you have various chunking strategies. But the idea is that each chunk has a vector embedding associated with it. And you might have a hierarchy in those embeddings, in the sense that certain documents contain chunks and certain chunks are related to other chunks. But in any case, you compute an embedding independently for each of these chunks. And that is what is used to plug into a traditional RAG system, where a query comes in natural language, the query is vectorized and matched, you find the nearest similar value in the data using the vector embeddings, and you receive a response. So let's define what we are calling Graph RAG exactly. In essence, Graph RAG is just extending traditional RAG by incorporating a graph as part of that workflow in the retrieval step. And it's very similar to what I just showed previously, which is you do have vectors in the process. You do have vector embeddings, and you also have a graph as part of the retrieval pipeline. The way the graph is incorporated may vary based on the architecture being used and what approach you're using, but the idea is that there is some level of connection or relationship between the nodes in the graph that represent entities in the data and how they're related to the chunks that the data came from. But going back to the framework of thinking, we want to say that in any system that uses this approach, the question we need to first ask is, what is the graph? The graph is essentially a collection of nodes and entities, nodes and relationships. And these nodes represent entities that exist in the data. And the next question we need to ask is, how is the retrieval done in a way that's different from what we call traditional RAG? Let's also understand a little bit about how graphs enhance unstructured data to begin with. Inherently, graphs are object-oriented in the sense that they represent entities or objects in the real world via nodes and how they are connected via edges. So it's a way of representing your data. They capture the relationships between the entities explicitly. And the word explicitly is important because when you look at the way traditional RAG is done, the relationships between entities in your data are implicitly captured via the embeddings, but the graph in this case makes that explicit. And why is this important? It's because traversing the vicinity of any entity or a node in your graph is quite natural and quite easy. Graph data model is a good fit to add structure to your related entities in the unstructured data. And the way we express that structure is through an something called triples, which is basically a collection of subjects, predicates, and objects. I'll explain a little bit more using an example. And the benefit of a triple is that it can be represented as simple sentences, which is very useful to generate added context. So let's go over a bit of brief history in terms of where the term RAG and graph RAG came from. The primary sources for where the term Retrieval-Augmented Generation came from are from these two papers by Google and Facebook in 2021 and 2020. And the term Retrieval-Augmented is what was new in these works, in the sense that we are using the generative capabilities of LLMs, but also augmenting them with retrieval from a custom backend. The first time the graph RAG terminology was introduced was roughly in September of last year, 2023, in a blog post by Nebula Graph, where they actually mention how they use RAG in conjunction with knowledge graphs. And if you're following the trends in graph RAG lately, the most common mindshare item that people are talking about a lot is the Microsoft paper, From Local to Global. And this is currently the most you could say, widely known form of graph RAG, though by no means is it the only way to do graph RAG. And for the purposes of this talk, I'm not going to be going over this architecture because it's very elaborate and is very, very specific to the way Microsoft implemented it for their research work. I'll also mention another key term that's emerged in the literature in the last couple of months. It's called hybrid RAG. And if you're familiar with search and retrieval, you're likely familiar with the term hybrid search. The term hybrid RAG, however, is not the same as hybrid search. Hybrid search is a combination of keyword-based search and vector search. But hybrid RAG is being used to describe systems where you build RAG, but you combine multiple retrieval methods. And there are some very interesting blog posts that describe how graphs can be used in the different stages of RAG, one by yhow.ai, and another one by Louis Guiton, who also introduced the term hybrid RAG in his blog, where he explicitly separates vector RAG from graph RAG from structured RAG and uses the term hybrid RAG to combine various forms of these entities. So the idea of hybrid RAG is kind of been around, but what happened recently in the last month is there's been tangible evidence of graphs measurably improving RAG, and this is in practice. It's not a work of research, but more a real-world use case. And this is from the paper by BlackRock and NVIDIA, and I want to unpack this paper a little bit more so that we can understand what's going on under the hood and what graphs are exactly doing. The paper's title is Hybrid RAG, and I won't go into the numbers, but in a nutshell, the results of this study showed that the hybrid RAG system does better than the individual systems that use vector RAG alone or the system that retrieved from the graph alone. So the combination of those two systems is what improved results on average. So let's unpack this a little bit because it's worth understanding what exactly the graph is doing and why it is useful. So we'll go back to the framework that I just mentioned, which is what is the graph? What are the nodes and edges based on this data set? So the data set that was used in this study was a set of earnings reports from BlackRock's data set. And on the left side, you can see that there's a stage one of this process in terms of how they construct the graph. Stage one is they use the chunks of data from the earnings reports. They perform a pre-processing step using an LLM prompt, and they clean that text. Essentially, the cleaning process involves generating abstract summaries of the data and cleaning the data in a way that makes it more relevant to the downstream task. So it's kind of like a way of summarizing and shortening the data and not having extraneous information. And I'll explain this with an example in the next slide. But following this, there's step two, which is where they actually extract triples from the graph. And a triple, as I mentioned, is a collection of subjects, entities, predicates, and objects, and that represents a node or an edge in the graph. So they produce a knowledge graph using this workflow, using a combination of a two-stage step in LLMs, and that is what is used in conjunction with vector search. So let's go over this with an example. It'll make a lot more sense. So let's say you have this data set of some summary of BlackRock earnings reports. And in this case, they're talking about the CEO, Larry Fink. In chunk one of this data, you have information about Larry Fink himself. And then in chunk two, you have information about where he's born, and you have n number of chunks in the data. So what their preprocessing step looks to do is they attempt to reduce the verbosity in the text and also make it more pointed towards what entities exist in the data. So as you can see in chunk 1, we are explicitly isolating the sentence, Larry Fink is the CEO and co-founder of BlackRock, which is a useful sentence in itself. The next sentence captures the fact that BlackRock was established in so-and-so year, 1988, and so on. So this way, you have processed chunks that contain much more concise and relevant information for graph construction. And then the third step is actually extracting the triples from the graph. And this is also done using a separate LLM prompt, where you use the processed chunk information to create a subject, predicate, and an object. Or you could just say that each end of this, the first and the third item is a node, and the one item in the middle is a relationship or an edge. And a collection of these triples is what forms a knowledge graph. Now, we recall from our framework that we know that graphs can model simple sentences via these triples. And this is what it might look like in practice. The same data that we had, the chunk extraction process, where we actually convert the chunks into triples, relevant triples in the graph, can be used to actually construct a knowledge graph of this form, where you actually have explicit links between the person Larry Fink and the other entities that he's related to, his place of birth, the company, and so on, including the nature of the relationships between them. So the key benefit here is that the information that might have been in disparate chunks of your data, it might have been separated in space. You might have had one fact in chunk 1 and another fact in chunk 25. In the graph, they are directly next to each other. The other benefit is that triples are a form of basically capturing the essence of the chunks in very simple sentences. And finally, we can now put together all this data into a database system where you can query it using a query language. So this is a really powerful aspect of what graphs are doing. So the whole point of doing all this is so that we can do a retrieval. And then we ask the question, how is the retrieval process here different from what a traditional RAG process would do? So let's ask the question, who is the CEO of BlackRock and where were they born? Now, this is a natural language question, and you would expect a response that uses the facts in the data. So the traditional vector retrieval process is done as you might normally expect, which is you transform this query into a vector embedding, and you perform a similarity search on your data. You return the top k results, and in this case, because you have the terms CEO, BlackRock, and born, you're going to get similar text from the different chunks via the similarity. But what the BlackRock hybrid RAG approach does is it also has an additional step, which is the graph retrieval process. And they also retrieve data from the knowledge graph that is underneath this, the RAG system. And they don't explain explicitly how they do the retrieval, but one common way of doing a graph retrieval is using a text-to-cipher pipeline. Cipher is a query language for graphs, so your LLM can actually generate the cipher query and retrieve the relevant information, in this case, the triples that form the data itself. So the key point we're trying to make here is that the way the hybrid RAG approach works is you obtain the context from the vector database and you obtain the context from the graph database, and you concatenate those. The combination of this provides the generation LLM more context, and that's what allows it to generate the response that Larry Fink is the CEO of BlackRock and he was born in Los Angeles. So you can imagine scenarios where you might have a question where the facts are actually quite far apart in the text, and you may have mentions that are not as clear in the text as something as explicitly saying Larry Fink was born in Los Angeles. And that's exactly where the graph is useful, because it explicitly provides the context to the generation model in a way that it might have missed via pure vector retrieval. So this is one retrieval strategy that I mentioned, hybrid RAG. The other common way people use vector databases and graph databases or retrievals side by side is you perform the graph traversal downstream of the vector search or a hybrid search. And the benefit of that is that you first narrow down on terms that are semantically similar to the query that you have. So you identify chunks of text that are relevant, but then you link the chunks to the the nodes in the graph. Once you have the node IDs, you can then traverse the vicinity of those nodes in the graph to actually inform the retrieval process, and you get a much better context for the generation model. So it's kind of like a sequential approach as opposed to a concurrent approach as used in hybrid RAG. And of course, there's Microsoft's local to global graph RAG paper. They use a semantic clustering approach, which is way more elaborate and has many, many more intermediate steps. So, which is why I didn't go into it in this presentation. But in a nutshell, there are many such methods that are being published in the last few months. And it's just a trend that graph RAG is becoming, you could say, more mature, while also opening up new ways of thinking about combining different retrieval systems together. And of course, we haven't even gone into how you might use agents and prompt tuning methods, query expansion or query rewriting methods to enhance any of these stages. But the idea is that you would want to start with a relatively simple hybrid approach, like what was shown in the BlackRock paper, and build upward from there. And I want to highlight a little bit about the role of databases, because I feel like a lot of implementations of graph RAG seem to just use graph libraries to do the computation. And it seems to be the case that the reason for that is graph databases tend to be viewed as extraneous or an additional piece of infrastructure that is hard to maintain and add to the workflow. So I'm kind of peeling that layer apart a little bit in this slide. So the first thing to remember is that graph construction is an iterative process. When you construct a graph, it's very rarely complete, and it needs to be built over time. You normally have new data that comes in, and over time you might evolve the graph itself. And there's also a data pre-processing stage in a lot of these workflows. So while you're exploring the data to find out what's missing and what holes exist, graph databases are a very useful tool to visualize some of these steps and aid in this process. And importantly, the database offers a strong persistence layer so that you can actually maintain and manage the graph data, as opposed to just collecting the graph on demand and then throwing it away and potentially losing information over time for future context. And most importantly, scalability. It's baked into a graph database's design. A lot of graph libraries like NetworkX don't scale that well to large graphs, and real-world data is always bound to grow over time. So thinking about scalability and how to build a persistent graph that can scale is a very important part of this process. And I want to highlight that databases themselves are evolving alongside RAG. If you ever worked with RAG, you've likely heard of DuckDB and LanceDB, which are relational and databases and vector databases, respectively. They're both really popular tools, very easy to install. And I'd like to mention that Kùzu, which is a company I work for, is a complementary solution to these tools in the graph space. All of these systems are embeddable and focus on ease of use and setup. They're highly interoperable with the data ecosystem, all the way from databases to data lakes to data frame libraries and data warehouses. And most importantly, they're permissively licensed, meaning that they're open source and you can build proprietary applications on top of them. The other common misconception is that embedded tends to be conflated with small scale or slow. I should add that all of these three solutions, DuckDB, Kùzu, and LanceDB, are known to be very, very fast and highly scalable. So these characteristics that I just mentioned don't preclude performance. They're actually very much alongside the performance aspect. So I won't go too much into the usability features of Kùzu in depth, but in a nutshell, Kùzu is a property graph database. It has a property graph data model, but also has support for an RDF data model if you work with RDF data. And it supports the Cypher query language, which makes it amenable to LLM-based workflows, because LLMs can generate Cypher. It's also embedded and very similar in philosophy to DuckDB and LanceDB. And it's fully ACID compliant, it's permissively licensed with an MIT license, it's interoperable with many formats, and it's integrated with the ML and AI ecosystem, namely NetworkX, PyTorch Geometric, and of course LlamaIndex and LangChain. So you can feel free to go to any of these tools pages, for example LlamaIndex, and check out Kùzu there. So I already covered the interoperability and scalability part, but why it makes sense to use a database like Kùzu for a graph RAG system is that you can model your data as property graphs, which is the most commonly accepted graph data model, while also imposing structure on your data. And unlike other graph databases, Kùzu imposes a structured property graph model and has a strict schema, which is really helpful in data management and maintenance of your data model over time. You can also combine your property graphs with domain-specific RDF graphs while still querying the whole system in Cypher. And you can also add a persistent graph layer to your graph RAG methods when you have advanced methods like GNNs, node embeddings, and if you're using graph algorithms to enhance the process. And the reason why this is useful is seamless interoperability with libraries like NetworkX and also PyTorch Geometric. Kùzu directly serves as a backend for PyTorch Geometric, so you can directly run your machine learning pipelines on a persistent graph backend while persisting the features to disk. I'll quickly touch upon graph construction, where quality is a big bottleneck, and entity resolution is a big term that's being used these days, where it's very challenging to construct high-quality graphs, especially when you're extracting the data from unstructured text. And this is an example of names of persons and their addresses, where they're pretty much on the right side, they're all the same person, named slightly differently. And the role of the entity resolution model or step is to resolve these entities and tell the graph that these are the same entities. The reason this is important is retrieval performance can disproportionately affect the generation outcome, which impacts the quality of your RAG. So it's very important to focus on good quality retrieval. And for this, entity resolution is a key and necessary step in many cases. I'd like to add that Kùzu regularly interfaces with companies like Sensing via their API and SDKs and desktop tools for performing entity resolution. Hats off to them for what they're doing. And also Yha.ai, which is another company, has a knowledge graph studio platform, which is a graphical user interface for entity resolution. So I recommend checking these companies out and their websites for their offerings. So I'm going to end by saying that graph RAG is not a monolith. Don't think of a graph RAG system as just retrieving from a graph. Typically, graph RAG involves graphs and vector search. And they can be combined in various ways, differently even than what I've explained here. But the idea is more or less the same, where you use many different components in the indexing and the retrieval stage. And it's important to know that each stage can be built and tuned independently. So while building these systems, it's recommended to design concrete evaluation strategies, which themselves evolve as we go through this space. And as I mentioned about the framework earlier, when thinking about graph RAG, it's important to qualify how and where graph RAG is being used and whether or not there exists a persistent storage layer. And if there doesn't exist a persistent storage layer for the graph, it's worth asking why. Why was the graph not persisted? Is it because it was not necessary, or the graph was actually not being utilized in a way that was growing with time? So ask these two questions. What is the graph in graph RAG? What do the nodes and edge represent? And how is the retrieval process different from traditional RAG? And the more this tooling evolves and improves, it's likely that graphs will become core components of modern RAG systems. And I'll end by saying there's a lot of interesting open source projects going on in the graph RAG space. So I highly recommend taking a picture of this slide and going through these GitHub repos. All of these are open source projects. And just to make things easier, I've linked to the exact issues on these repos that are specifically focusing on graph RAG. A lot of the community is participating in these discussions, building these solutions. And some of these are frameworks, some of these are tools. But all in all, I think there's an active community building around open source tools that can build graph RAG systems. So I highly encourage developers in the audience to get out there and start building. So yeah, I'm wrapping up with this. I just want to end by saying Kùzu is an open source database, graph database. You can check us out on GitHub, and we also have an active Discord community that you can check us out on, where you can talk more about your graph use cases. So I've linked to our Twitter page and the LinkedIn pages. We're Kùzu Inc. on LinkedIn. So please follow us there, and yeah, I'm looking forward to chat more with people who are building in this space. And yeah, I'm available after the talk as well for additional questions.
And thank you, Prashanth. We do have a question question. We do have a couple minutes for questions. So there's Jelson over there. Make eye contact with the gentleman over there. Okay. All right, that's fine. Yeah. So we'll take these questions, and that's it. That would be.
Okay. One thing was that for the graph RAG, if like I want to remove certain knowledge after it's got added, or like there is a new knowledge that overlay with the old knowledge. So for example, in this earning report, A was CEO of this company, but in the subsequent is this change. Is there any efficient way to remove and update the graph knowledge? And the second question is that for graph knowledge, like what is your best practice? Graph RAG, like what your best practice for partitioning the data? Like in the vectors DB, you need to partition it like in certain case for multi-tenancies as well for certain like domain knowledge. What is the best practice for partitioning in graph RAG? Thanks.
Yep. So I think the first question was about how to update the graph efficiently, right? So updating graphs is a very straightforward process. Just like you have in relational databases, insert or merge or whatever the keywords are, you have an option to extract the raw data as triples and then either overwrite or like update the graph itself, or maintain a version of the graph. You can have an old graph and a new graph and track the change of the graph over time. So modern graph databases offer these, you could say, CRUD features that allow you to maintain the versions of the graph. And then the second thing is, I believe, partitioning. So as far as I see, graphs themselves scale reasonably well on a single node. And actually, Kùzu is a single node system. So this is not a distributed system where, in the sense that the use case is not distributed, where you need to have multiple portions of the graph on different servers. The whole graph itself grows organically from a single node. And ideally, the way this would work is the graph augments or enhances the vector search. So it's not meant to be used in isolation. So I can talk more about specific cases where scalability challenges are addressed, but by and large, it would not be the bottleneck. You don't require partitioning of the graph.
Last question.
So you mentioned entity resolution.
Yeah.
So is the idea like define the vector similarity and then flag them for a human to then go and resolve and see if these are the same entities or not?
Yeah, so the question's about entity resolution and whether it involves vector similarity. So no, that's not what I meant. So when I say entity resolution, it's specifically on the entities or the nodes in the graph. So the idea here is that you might have two nodes that represent the same person, but the underlying information or the properties on that node are not the same because they came from different sources. So the idea is, how do you resolve them? And what an entity resolution tool does is it provides you the means to either merge those two nodes together into a single node because they represent the same entity from the real world, or you can have a mapping in the sense that you know that these nodes are connected. They are essentially aliases of each other. So depending on the workflow, you would do one or the other. There is no relation to the vector side of things. The algorithms used in entity resolution are specific machine learning algorithms that are trained for the purposes of merging these entities.